Okay, I guess we'll get started. Thank you all very much for showing up. My name's Caleb Hurd. I'm with the rental and rapid response group out of Zeeco, and then Clayton, he'll introduce himself in a little bit. But what we're here to talk about today. Well, I acted like it was gonna click, but okay, there we go. But main thing is flares, the emissions, and how do we control those and help minimize emission. And so one of the challenges is upstream industry. So the well site, shell plays. And this first video is a picture of a flare that is in operation according to the control system. So the pilots are lit, everything is as it should be according to the control system. But as you can see, the picture on the left, there is no flame. The one on the right is a FLIR image showing where it's venting. And this is, in particular, this is an air flare. And so, as most in industry will know, there's a challenge with over airing or over steaming and over application of assist media. So how do we prevent that? And so this is, part of the TCQ testing that took place several years ago. Zeeco also did some supplemental testing. And as you can see, there's a precipitous fall after you get to about 600 to 700% stoichiometric air for an air-assisted flare. And so as you drop off that, it quickly decreases below the 98% threshold that you would expect for a properly operating flare system. So this is a curve of typical flow rate at an upstream facility. As you can see, it drops off rather significantly after 6 months and a year to where very quickly the actual operating conditions are changing. So if we put in just a single speed flare or a single speed blower at these rates, you can see that nothing changes. They're operating at full horsepower all the time. Versus if we have a pressure switch or a flow switch and they've got a simple 2-speed blower, now you can see as the flow rate from the going to the flare drops off, they can actually turn the fan down and get it down to 50%, a little bit of turn down. And that's the gray. Piggybacking on that, if you add a flow transmitter or pressure transmitter, something to monitor the flow, now you can ramp it up and down with a VFD. And if we just do a simple step curve, every 10%, you can see once the flow drops down below those capacities, the fan also ramps down. And then lastly, direct control. So if you can monitor the flare and you have a 4 to 20 basically output to control the fan speed, now you can get very closely to what the actual flare is seeing. Now, operating expenses. So if you just have a flat, 100% speed, single speed blower, you can see on a 5 horsepower blower, that adds up to about $5,000 a year. And as you go to central gathering facilities, midstream plants, if you kept that same thing, you're going to have a very high cost of operations. Conversely, if you do just something as simple as a lookup table or direct control, now you're getting, a 90% reduction almost, or 80%. So the return on investment for adding those additional controls, hey, it pays for itself. So that's great. Let's do that. But sometimes you have to do that CapEx spending. It's $3,000 to $30,000 depending on what you install at the facility, but it can quickly pay for itself is the grand scheme. Now, looking at a couple of different options, we see in upstream facilities, there's a propensity to buy standard equipment. So first is a custom designed system. And so we'll go back through that same curve, that same capacity curve or operating. And then the inverse of that, as you can see over in the far right-hand corner or the right-hand side, is the percent stoic air. And so as we saw in that first couple of slides, if you have an over application of air, that you're going to have a reduced destruction efficiency. And so if it's custom design right on point, you can see it basically at the end of the year, they're stepping up to that 600% stoic air, and they're going to see a reduction in destruction efficiency after that. The 2-speed blower, that helps you. That gets you at least to where, hey, you're still within the operating parameters. You're still going to be meeting that 98% destruction efficiency. And then the lookup table or the direct control, now you're really dialing in exactly where you need to be, and you're well outside that, that threshold. Now, if you do a standard design, and this is where we see end users or engineering companies just trying to get a quick fix, get something there out on the facility that operates, and they don't care if, say, it's twice the capacity of what they need. Now, the issue is now your design capacity is at 50%. And so we go through those same models, and now on a single speed blower, you're well below that 98% threshold. You're above 600% stoic air. And so not only is the cost something that helps you, but the emission impact, you're basically not meeting regulation. So even though your flare, the pilots are showing lit, you're not operating where you need to be. So just a parameters kind of showing what happens. If you can just put a VFD on it that gets 10-to-1 turn down, you know, on your flare turn down, you're talking almost 170-to-1. So that really helps. And you'll see as on larger facilities, sometimes there'll be 1,000-to-1 turn down is what's required. And so just a simple VFD on a single blower is not sufficient. Turn down's also greatly affected by your composition. So we've been assuming that you're seeing a constant composition go into the flare stack. And that may be true on an upstream facility. It's pretty regular, but as you go to a processing plant, you have different reliefs, you're going to have different compositions. You know, do they have a single VFD set point? So this one had a VFD on it, but it just had a little potentiometer, or they'd control the set point. And as you can see, there's a little flicker of flame, but this was the same flare operating the same thing, and there's just a change in flow rate. And so they didn't speed up or slow down the blower as needed. And so you get good combustion efficiency on the right, but on the left, it's right there on the threshold of actually going out and being venting. And then lastly, turn down control issues. I mean, what we see on these upstream facilities is that, you know, you have plugging of flame arresters, or just general condensate problems, scale in the line. And so if you have your normal pressure control, that you can foul these, and now you're sensing a high pressure, high flow on the upstream side of the arrestor, and now your VFD speeds up when it does not need to speed up. And so that's a challenge. Flow sensing, same thing. It does not keep up with changing compositions as you go to a multi-stream flare. And then measuring atmospheric vapors at the low tank batteries and stuff, it's very hard to sense those and to control your flare accordingly. And so the lookup table sounds great if you can actually give it good inputs. And then lastly, percent stoichiometric air requirement for smokeless operation is not fixed, and it's dependent upon flare design, size, and operating conditions. So it's real easy to put it on a chart and say, theoretically, this is where you need to be, but how do we control to that? And so now I'll turn it over to Clayton.
And I work in aftermarket, what we call the engineered solutions group. So what we're trying to do is help operations meet new specifications, new environmental specifications, and get the most out of the equipment that they have. And that's the point. We've known that better controls is going to enhance combustion, enhance operation. But we've tried to do this or have this meeting to show that you can monetize these improvements and have sufficient payoff period. When we're flaring, we're so interested in making sure that we have good combustion efficiency, that we have a good flame quality. And for the most part, the industry has taken a very indirect or a proxy method to that. The tried and true vast majority of operators are using ratio control, whether it's steam or air injection. What that means is they measure the flow rate for a flare flow, and then inject some proportion of steam or air. And that's led to quite a bit of insufficient combustion efficiency and poor operations. So this is 10 years old at this point, but TCEQ and the EPA investigated, well, should we set parameters? Is there a good parameter for what steam to hydrocarbon ratio results in good combustion efficiency or prevents bad combustion efficiency? Maybe not a single one, but what about a range? And result of that testing is a scatter plot. There really was no single association or band of combustion of steam to hydrocarbon ratio that ensured good smoke-free but high combustion efficiency operation. It's got many, many variables to it. Primarily, what's the composition of the gas? Different gases and different compositions require different steam and air inputs for smoke mitigation. But other than that, there's where is this flare being operated in its range, and what is the technology and in other aspects. And so while this is the absolute most common method for controlling steam or air injection is a ratio control, it's also one of the least accurate. One of the ways that I discussed it being inaccurate is the turndown problem. Flares almost all the time are operated at very, very low normal flaring rates. And when you're talking about steam, there's a huge kinetic component to how much steam is required. You need the velocity, you need the pressure in order to aspirate the air and to mix the air to create smokeless flaring. So when you have sufficient flow and pressure of the steam, no problem, you can get on a very linear portion of this steam control curve. But where do we operate the vast majority of the time? Down here in the lower 1/10 or 1/5 of the operation range, where there is no kinetic energy, and you're going to have to overcome that with a higher injection ratio. So this results in, while most people are using a simple steam to hydrocarbon ratio control, leads to a lot of inaccuracies and chronic over aeration. Too much steam, too much air normally. Also turns into this proxy method. Instead of directly controlling based on what the flare flame needs, controlling based on indirect measurements is more complex, lots of different inputs, outputs, and compounding errors. So you're not trying to inject with the understanding of what the combustion zone or what the actual flame looks like. You're measuring flare flow, making calculations, assuming what the steam or air injection needs to be. Trying to maybe you enhance that measurement with understanding what the properties of the gas are, and then feedback to what your steam valves are. This is a very, very common configuration for NHVCZ measurement. NHVCZ measurement, while it's an operation parameter, it's not a good smokeless control parameter at all. And there seems to be some industry confusion over that. So philosophically, a better approach is direct control. Direct control being look at the flame, understand the quality of the flame, and adjust your smoke mitigation accordingly based on the flame inputs. There's one method that we've done here with a dual wave infrared monitor, the Zeeco Contour, which takes a look at two different infrared wavelengths that give us a general quality of the flame. And you don't have to, regardless of what the flare flow is, regardless of what the composition is, we can understand what the quality of the flame is and control by that parameter only. Successful at mitigating smoke, having some opacity in your flame is not a good quality that you want. But more importantly, to environmental impact, it can understand over aeration. And so this is a very, very simple device. It's not the Flare Guardian or the Mantis or Mantis Lite. Those that have much more capability to this. This is a very simplified approach. If you need other parameters, there are other monitors that provide a lot more input. This has really one control parameter of flame quality. And what it's doing is two simplified or two infrared inputs that equate. One really understands the carbon in combustion, and the other is looking generally at the oxygen in the combustion zone. It makes a ratio. So that ratio, independent again of what the flow rate is, independent of what the composition is, needs to generally be the same. And so if you control to that right ratio, you're going to have generally good flame quality. A carbon heavy ratio or a higher ratio means that you're on the verge of smoking. But more importantly, too low of a ratio indicates you're over aerated. There's too much air in the combustion zone. You're risking dilution. And so when you control to the ideal ratio, not only do you have the right flame quality, but that also results in your highest combustion efficiency. And so what we did was, again, we're trying to help people understand, operators understand, how do I monetize these kinds of controls? And this comes from a example this year in an oil fence plant here in the USA, where one of these devices was deployed, and we spent some time tuning it. And so what we wanted to capture is a small oil fence incursion at a facility. And so it has its baseline flow. It had some kind of upset, not huge, 5,000 pounds an hour. And then that was curtailed within the plant and kind of brought it back to baseline. There's some qualities about this incursion that I want to talk about. The incursion was an olefins and nitrogen release. So you've got some things that like to smoke, and you have some things that the nitrogen needs no smoke mitigation. And as that initial flow was curtailed, eventually the olefins kind of bled out of that system, and we got back to just a natural gas purge, which is really, really common. So we have two really important process changes that occur in this single event. This is an estimated control overlay of steam to hydrocarbon. So it's really easy to do. You measure, the flow measurement will indicate how much flare gas flow there is, and then have that ratio, in this case, about 0.4 steam to hydrocarbon ratio. And so that steam injection follows really closely what the actual measured flow is, and goes in parallel pretty well. The problem is, as the nitrogen was pulled out and we got to a lower rate, we see this many, many times. The event is largely over, and operators can now concentrate from whatever process they were trying to control to somebody finally looks at the CCTV and realizes that I've mitigated the flow, but they're still trailing smoke. And it's because there's residual oil fins left in there. So what handle does the operator have? The input that he has is a steam to hydrocarbon ratio, and he needs to adjust it up. So he changes it from 0.4 to 0.5, and he sets it there. And you can see the bump up in this injection rate as a result of that manual input. From that point forward, there's no impetus to make any other change. There's really no driver for that operator to really try and see how little steam can I really inject and still maintain smokeless but good flame quality. And so henceforth and forevermore, we've changed what our normal input is, and we have a steady state operation that chronically is using too much steam. When you deploy a direct measurement device, in this case, the contour, we see a couple of advantages. Number one, the incursion had inerts in it, had a lot of nitrogen, which means we don't need as aggressive a steam to hydrocarbon ratio. We don't ever employ quite as much steam. More importantly, where the ratio control allowed for some smoke and required a manual input, a direct control device measuring the flame quality and understanding if there's opacity maintains enough steam injection that it never smokes. And as the oil fins are finally kind of bled out of the system and we return to a natural gas steady state, just a purge or a sweep gas, we've returned to the original steady state of injection. And now you have a delta. It's not much. This is a small flare. This is a small instance, but you have continuous savings of 150 pounds an hour, hour by hour, day in, day out. And so this is where the monetization comes in. If you assume a couple of things, using a calculator of $8 per 1,000 pounds of steam generation is one method. Caleb just talked about it. It applies to the VFDs as well. With the direct control, you're saving on electricity for operating at that much lower frequency, lower horsepower. This is kind of a baby example. We're only showing a $10 delta in this incursion. But the key is the steady state. What we see over and over is people leaving it at this marginally higher steam injection rate as a normal operating practice. So flares, the vast majority of the time, are operating at steady state minimum purge injection rates. So 95% of the hours of the year at this 150 pound an hour steam savings actually turns into enough money to buy the hardware for direct steam control. And this doesn't include other incursions. And this is only a measurement of the steam savings. There's many, many other residual savings. If this is a facility that has to comply to combustion zone net heating value, there's a possibility that for every pound of steam that they're injecting, they need 1/3 pound of fuel gas enrichment in order to achieve the NHV, the proper NHV-CZ. So there's potentially quite a bit of savings in fuel gas enrichment, as well as the longevity of the equipment and other impacts. So with the most simple and rudimentary calculator, we can see direct control is a method that can pay for itself within a single year, very, very simply. Again, ultimately, we're looking for more precision, quicker feedback, and in ensuring good flame quality for no smoking, but more importantly, higher combustion efficiency. And that's what we hope the operators are able to do. Any questions with that?